Right now, as you're watching this, whether you're in New York, Texas, California, Florida, or somewhere in between, the ground beneath your feet is moving faster than it was a few years ago. Not metaphorically, not politically, physically. The planet itself is rotating slightly faster. Days are getting shorter, not by hours, not by minutes, but by milliseconds. Tiny fractions of time so small you would never feel them. And yet, those fractions are large enough that the most precise clocks humanity has ever built are noticing. Atomic clocks are drifting. Satellite systems are compensating. Navigation networks are recalculating. And scientists have confirmed it. Something has changed about Earth's rotation. This is not a conspiracy. It's not a headline trick. It's measured by global timing laboratories, space agencies, and geophysical observatories. For decades, Earth's rotation had been gradually slowing down, largely due to tidal friction from the Moon. Then, unexpectedly, the trend shifted. Over the past few years, Earth began spinning slightly faster than it has in roughly half a century. Some of the shortest days ever recorded with modern atomic precision have occurred recently. And while the change is subtle, it is real. The question is not whether it's happening. The question is why. Because when a planet changes its rotation speed, even slightly, it means mass is being redistributed. It means forces are shifting deep below the surface. It means ice is melting, oceans are moving, the core may be behaving differently, and the delicate balance between gravity, angular momentum, and internal structure is adjusting. Earth is not a rigid rock spinning in space. It is a dynamic system, fluid, layered, shifting constantly. If this is the kind of science that matters to you, the kind that affects navigation systems, climate patterns, satellite networks, and even financial timestamps, like this video, subscribe, and tell us in the comments which part of the country you're watching from. Are you on the West Coast, the Midwest, the Gulf, the Northeast? Every place on this planet is riding the same rotating sphere. Let us know where you're standing as it turns. Now we begin. To understand what is happening, we need to start with something simple: how long is a day? Most people would answer. But that is a definition, not a measurement. A day is defined as 86,400 seconds. But those seconds are not based on Earth's rotation anymore. They are defined by atomic clocks, specifically by the oscillations of cesium atoms. An atomic second is the duration of 9,192,631,770 transitions between two energy levels in a cesium-133 atom. That number does not change. It is stable, precise, and independent of planetary motion. Earth, on the other hand, is not perfectly stable. Historically, humans measured time by the sky, sundials, star positions, the apparent motion of the sun. But as precision increased, especially in the 20th century, scientists realized that Earth's rotation fluctuates, not dramatically, but measurably. Variations of milliseconds occur due to atmospheric winds, ocean currents, seismic activity, and interactions between Earth's layers. For decades, the long-term trend was slowing. The gravitational pull of the Moon raises tidal bulges in Earth's oceans. Because Earth rotates faster than the Moon orbits, these bulges are dragged slightly ahead of the Moon's position. That creates a torque, a subtle braking force, that gradually slows Earth's rotation over geological time. Millions of years ago, days were significantly shorter. During the time of the dinosaurs, a day was roughly 23 hours long. Even farther back, it was shorter still. So the expectation was clear: Earth should continue slowing down. But in recent years, that expectation has not held consistently. Highly precise measurements from very long baseline interferometry, an astronomical technique using radio telescopes across continents to measure Earth's orientation relative to distant quasars, have shown that some recent days were shorter than the standard 86,400 atomic seconds by more than a millisecond. In fact, some of the shortest days ever recorded since atomic clocks became standard occurred within the past few years. A millisecond sounds insignificant, but consider this: global positioning systems, financial markets, telecommunications networks, and power grids rely on synchronization accurate to microseconds or even nanoseconds. When Earth's rotation drifts relative to atomic time, adjustments must be made. That is why leap seconds exist. When Earth slows down enough that astronomical time drifts behind atomic time by nearly a second, a leap second is added to keep clocks aligned with the planet's rotation. Now scientists are facing the opposite possibility. If Earth continues spinning faster relative to atomic time, a negative leap second may eventually be required, something that has never been implemented before. That alone tells you this is not routine. So what is accelerating the planet? The answer begins beneath your feet. Earth's interior is layered. At the center lies a solid inner core composed primarily of iron and nickel. Surrounding it is a liquid outer core, also iron-rich, thousands of kilometers thick. Above that sits the mantle, a vast region of semi-solid rock slowly convecting over millions of years. And finally, the crust, the thin, brittle layer we live on. The liquid outer core is not static, it flows, it churns. It generates Earth's magnetic field through a process known as the geodynamo. That molten iron moves in complex patterns influenced by heat escaping from the inner core and by Earth's rotation itself. When mass shifts inside a rotating object, its rotation speed can change. You can demonstrate this with a simple experiment. Imagine a spinning figure skater. When they pull their arms inward, they spin faster. When they extend their arms, they slow down. This is conservation of angular momentum. The distribution of mass affects rotational velocity. Earth behaves similarly. If mass moves closer to the rotational axis, rotation speeds up. If mass moves farther away, rotation slows. One of the major contributors to recent changes is glacial melt. As massive ice sheets in Greenland and Antarctica lose mass due to warming temperatures, that water redistributes into the oceans. This redistribution alters Earth's moment of inertia. In some regions, ice loss reduces mass far from the equator, subtly affecting rotational dynamics. However, glacial melt alone does not fully explain the recent acceleration. In fact, many models suggested it should contribute to long-term slowing, not speeding up. Which brings us back to the core. In recent years, research has suggested that Earth's inner core may not rotate at a constant rate relative to the mantle. Seismic studies indicate that the inner core can rotate slightly faster or slower than the rest of the planet over multi-decade cycles. Some evidence even suggests that it may have slowed relative to the mantle recently, or changed direction in subtle ways. These changes are extremely small, but when dealing with a solid sphere of iron over 400 kilometers wide, small adjustments can matter. If angular momentum is exchanged between the core and the mantle, the rotation of the surface can change. Think of it like two gears interacting. If one shifts speed, the other responds. Then there are atmospheric effects. Winds redistribute mass constantly. Seasonal shifts in atmospheric circulation, jet streams, monsoons, pressure systems, can nudge Earth's rotation slightly. Ocean currents, too, play a role. Large-scale oscillations like El Nido alter how water mass is distributed across the planet. Earth is not a rigid ball. It is a fluid system layered on fluid systems. Earthquakes can also change rotation speed. In 2011, the massive Tohoku earthquake in Japan redistributed enough mass to slightly shorten the length of the day by microseconds. Not milliseconds, microseconds. That event alone demonstrates how sensitive rotation is to mass movement. But none of these alone fully explain the recent cluster of record short days. Scientists are still investigating the combination of influences. It may be that core dynamics are playing a stronger role than previously recognized. It may be that climate-driven mass redistribution is interacting with deeper processes in complex ways. The key point is this Earth's rotation is not fixed. It is dynamic, and we are now measuring it with unprecedented precision. The implications go beyond curiosity. Global navigation satellite systems, GPS in the United States, Galileo in Europe, Beidou in China, depend on atomic time. These systems track satellites moving thousands of miles per hour, calculating positions to within meters or less. Even slight mismatches between atomic time and Earth rotation time require correction parameters. If negative leap seconds become necessary, software and infrastructure worldwide will need updates. Financial markets timestamp transactions down to microseconds. Power grids rely on synchronized alternating current frequencies. Scientific experiments depend on coordinated timing across continents. The modern world assumes time is stable. But time, as measured by Earth's rotation, is not perfectly stable. And yet it is important not to exaggerate. We are not spinning out of control. We are not heading toward catastrophe. The changes are small. Measured in thousandths of a second, there is no evidence of imminent danger. But the fact that Earth's rotation can measurably accelerate over short timescales reminds us of something fundamental. Our planet is alive with motion. Beneath the crust, molten iron surges. Above it, oceans circulate, ice sheets collapse and reshape coastlines. Atmospheres shift with seasons and storms. The magnetic field generated by the core fluctuates and occasionally weakens or strengthens. Even the length of a day, something so basic we build our entire civilization around it, is not constant. We will go deeper into the core itself. We will examine what seismic waves reveal about its structure, how scientists infer its rotation without ever seeing it directly, and what it means if Earth's deepest layer is behaving differently than expected. For now, understand this: the planet you are standing on is not static. It is rotating slightly faster than it did just years ago. The difference is invisible to your senses, but not to atomic clocks, not to satellites, and not to the instruments quietly measuring our world every second. Something unusual is happening, and we are only beginning to understand it. If the surface of Earth feels solid and permanent beneath your feet, that is an illusion created by scale. The crust we live on is thinner, relative to the planet, than the skin of an apple. Beneath it lies a world that is not fixed, not rigid, and not fully understood. To understand why Earth's rotation is shifting, why days are getting shorter, we have to go down nearly 4,000 miles into a region no human will ever physically visit: the core. At the very center of Earth is the inner core, a dense sphere composed primarily of iron and nickel. It is roughly 120 kilometers in radius, about the size of the Moon. Temperatures there rival the surface of the Sun, estimated around 5,000 to 6,000 degrees Celsius. Pressure is so extreme that iron remains solid despite the heat. Surrounding this inner core is the outer core, a thick shell of liquid metal about 200 kilometers deep. That liquid iron is in constant motion. We do not see the core directly. Everything we know about it comes from indirect measurements, primarily seismic waves generated by earthquakes. When a major earthquake strikes anywhere on Earth, it sends shock waves traveling through the planet. Some waves pass through solid layers. Others cannot travel through liquids. By analyzing how these waves bend, slow down, speed up, or disappear, geophysicists map Earth's internal structure. This is how scientists discovered that the outer core is liquid. Certain seismic waves, called S waves, cannot travel through liquid. When they encounter the outer core, they vanish. Other waves, called P waves, can travel through both solid and liquid, but their speed changes depending on density and composition. By studying these patterns across thousands of earthquakes over decades, researchers have built a detailed model of Earth's interior. But structure is only part of the story. The deeper question is motion. For a long time, scientists assumed that Earth's inner core rotated at roughly the same speed as the mantle and crust above it. After all, everything formed from the same rotating cloud of material billions of years ago. But in the 1990s, seismic studies began suggesting something unexpected. The inner core might rotate at a slightly different rate than the rest of the planet. The differences are extremely small, fractions of a degree per year. But over time, those differences accumulate. Some studies indicated that the inner core rotates slightly faster than the mantle, a phenomenon called super-rotation. Other research suggested that its speed fluctuates over decades. More recently, evidence has emerged that the inner core may have slowed relative to the mantle, or even oscillates back and forth in multi-decade cycles. This matters because Earth is not a rigid body. It is a system of interacting layers exchanging angular momentum. If the inner core speeds up relative to the mantle, angular momentum must be conserved. That means the mantle and crust may slow slightly. If the inner core slows or shifts, the outer layers may speed up. These exchanges are tiny but measurable with modern instruments. Think again of the spinning figure skater. When mass moves closer to the axis, rotation increases. When mass shifts outward, rotation decreases. Inside Earth, mass is constantly moving. Liquid iron flows in the outer core, driven by heat escaping from the inner core and radioactive decay. These flows generate Earth's magnetic field through the geodynamo process. Magnetic field lines rise from the core, extend into space, and shield us from solar radiation. The magnetic field itself is not stable. It shifts. It wanders. The magnetic North Pole drifts across the Arctic at varying speeds. Occasionally, in Earth's history, the magnetic field has reversed entirely. North becomes south, south becomes north. These reversals occur over thousands of years, and there is no evidence that one is imminent. But they demonstrate that deep internal processes are dynamic. Changes in the core's flow patterns could influence rotational speed. Because the outer core is liquid, it can redistribute mass internally. If convection currents strengthen in certain regions, if dense plumes rise or sink, the overall moment of inertia of the planet can adjust slightly. Recent research has suggested that the inner core may have entered a new phase of its rotational cycle. Seismic data comparing wave travel times from earthquakes decades apart show subtle shifts consistent with a slowing or even slight reversal relative to the mantle. The time scale appears to be on the order of 60 to 70 years, a multi-decade oscillation. Interestingly, this time scale overlaps with observed variations in Earth's rotation speed measured by atomic clocks. That does not prove causation, but it suggests a possible link. If the inner core is exchanging angular momentum with the mantle in cyclical patterns, that could partially explain why Earth's rotation has accelerated slightly in recent years. But the core is only one part of the system. Above the core lies the mantle, a region of semi-solid rock that behaves plastically over long timescales. It convects slowly, with hot material rising and cooler material sinking. These movements drive plate tectonics, the slow drifting of continents. When tectonic plates shift, when subduction zones move, when mantle plumes rise, mass is redistributed. Glacial rebound is another critical factor. During the last ice age, massive ice sheets covered large portions of North America. The weight of that ice depressed the crust beneath it. When the ice melted thousands of years ago, the land began to rebound upward, a process still ongoing today. This vertical movement redistributes mass and slightly alters Earth's shape. Earth is not a perfect sphere. It bulges at the equator due to rotation. The equatorial radius is about 21 kilometers larger than the polar radius. If mass shifts toward or away from the equator, rotation speed adjusts accordingly. Melting polar ice redistributes water toward lower latitudes, subtly influencing this balance. Then there are the oceans. Ocean circulation moves enormous volumes of water around the globe. Currents like the Gulf Stream transport heat and mass across basins. Seasonal changes in sea level, driven by temperature and salinity variations, shift weight distribution across the planet. Satellites like JURASS and RASTFO measure tiny changes in Earth's gravitational field caused by mass redistribution, providing data on ice loss and water movement. Atmospheric circulation also plays a role. When winds strengthen in one direction, they exchange angular momentum with the solid Earth. For example, strong eastward winds can slightly slow Earth's rotation, while westward winds can slightly accelerate it. These effects are small but measurable. The remarkable thing is not that Earth's rotation changes. It is that we can measure those changes with such precision. Atomic clocks define time with extraordinary stability. Very long baseline interferometry measures Earth's orientation relative to distant quasars billions of light years away. Laser ranging to satellites and the Moon tracks orbital positions to centimeter accuracy. Together, these tools allow scientists to detect variations in the length of a day down to fractions of a millisecond. Over the past few years, several of the shortest days since precise record-keeping began have occurred. The differences are on the order of 1 to 1.5 milliseconds shorter than 86/400 seconds. That may not sound like much, but in the context of geophysical stability, it is significant. It also raises a technical challenge: leap seconds. Since 1972, leap seconds have been added periodically to keep coordinated universal time aligned with Earth's rotation. Because Earth had been gradually slowing, positive leap seconds were inserted. But if the trend of shorter days continues, we may eventually require a negative leap second, subtracting a second instead of adding one. This is not trivial. Many computer systems are not designed to handle a second being removed from timekeeping. The possibility has sparked discussions among international timekeeping bodies about whether to reform or even eliminate leap seconds entirely in the coming decades. So when we say something unusual is happening to Earth, we are not describing a disaster. We are describing a measurable shift in planetary dynamics that interacts with the technological systems modern civilization depends on. And perhaps the most profound realization is this: Earth is not just a backdrop for human activity, it is an active participant. Its core flows, its mantle convects, its ice melts, its oceans circulate. Its atmosphere breathes in seasonal pulses. All of these processes intertwine. When days shorten slightly, it is not because something external has struck us or because physics has changed. It is because the internal engine of our planet is in motion, redistributing mass and angular momentum in complex ways. Scientists are still refining models to determine how much of the recent acceleration is due to core-mantle interactions versus surface processes like climate-driven ice melt. The answer is likely a combination. Earth's systems do not operate independently. The deep interior and the surface are connected through gravity, pressure, and momentum exchange. We will move upward from the core to the ice sheets and oceans. We will examine how melting glaciers physically reshape Earth's balance, how satellites measure gravity changes from space, and why climate shifts can influence the length of a day. For now, hold this image in your mind, a glowing iron sphere spinning at the center of the planet, liquid metal swirling around it, continents drifting above, ice melting at the poles, wind circling the globe, all of it connected, all of it in motion. The planet beneath you is not still, and the clocks are proving it. If science and the vastness of space captivate you, then your place is right here. Subscribe to The Boring Universe and come closer to the cosmos with every new video.